Physicists have been arguing for decades about what happens to information that falls into a black hole. Stephen Hawking suggested that it is destroyed, while others say it must survive in some way. They're both right, but only because they're asking the wrong questions. In fact, there are multiple answers to this question, depending on what you mean by information, and that has made the debate unnecessarily complicated. But now we can finally put this question to rest once and for all. This animation was made with the help of a university. Let's have a look. Whenever someone or something crosses the event horizon of a black hole, that could carry information about its properties like color, mass, electric charge, and so on. The key question is whether that information is lost forever or whether it can be recovered. If it's lost, we call this the black hole information paradox. Stephen Hawking argued that the information is indeed lost. Why? He said that if you wanted to measure what fell into the black hole, you would need to measure all the quantum properties of every particle that makes up that thing. You see, quantum mechanics says that everything that can happen does happen. So at any moment, a particle can be in two places or have two colors or whatever. It doesn't just have one property, but a whole bunch of properties that are compatible with the information that you have about it. That's why when you measure a particle, you don't know what it will be until you actually do the measurement. Once you've measured it, you've updated your information about it, and you know what it is. But then again, from the point of view of someone else who didn't measure it, the particle still had all those properties. This is called the uncertainty principle. There's a lot of information hidden in the uncertainty. Now, when you measure something, say with a meter stick, you don't measure every single property of the thing. You only measure the ones that the meter stick is designed for, say length. All the other information, say the exact composition of the material, remains unknown. So the information that you gain by measuring the length is always limited. And Hawking argued that this limit is set by the uncertainty principle. It tells you how much information you can get out of a system before you destroy it. Now, this means that you can never measure everything that falls into a black hole. Therefore, according to Hawking, you cannot measure what fell into the black hole at all. You can only measure part of it, which means you can at most gain some information about it, but you can never gain all of it. Hawking therefore concluded that information is lost behind the black hole horizon. It's not that simple, though. Other physicists have argued that Hawking's argument is wrong. Because he was too quick to conclude that you can't measure what falls into the black hole. The issue is that these people didn't bother to precisely define what they mean by measurement. You see, the problem with Hawking's argument is that it depends on the details of how you measure things. Yes, that's right. The way you measure it matters. You can always change the way you measure something so that you get more information out of it. For example, suppose you want to measure the spin of an electron. Just as with the meter stick before, you can't measure all the information contained in the spin because that would require infinite precision. But let's say you just want to know whether it's spin up or spin down? Well, then you can just measure the energy of the electron. Because spin affects the energy, you can basically read off the spin from the energy. You don't need to measure every possible property of the electron. In this case, you just need to measure one. So it depends on what you want to measure. To say that you can't measure anything about the electron just isn't correct. You can measure something about it, but you can't measure everything. And this is the crucial point that Hawking missed. The issue is that it's unclear what you should reasonably be allowed to count as a measurement. It shouldn't depend on the details of how you measure it. Otherwise, you could argue that no information is ever lost, because you could always find some clever way to measure it. But clearly, that's absurd. So we need some reasonable definition of what counts as a measurement. The trouble is that physicists haven't agreed on such a definition. For example, some physicists say that you can only measure information if you have a meter that you compare the quantity you want to measure to. This is what's called a classical measurement, but this is just a definition, and other physicists disagree with it. They say that quantum mechanics has its own laws and you can't just transplant the definitions from classical physics. They're right, of course, but that doesn't make their definition any less arbitrary. And this is why the black hole information paradox has been such a fruitful research area, because it forced physicists to think about what they mean by measurement and information. The result is that they came up with several different reasonable definitions. And each of these definitions has a different answer to the question of what happens to information in a black hole. We can sort the definitions into two categories. One category says that information is lost in a black hole, and the other says that it's not lost. Let me explain. The first category is that of the so-called von Neumann measurements. These are measurements in quantum mechanics in the usual sense. You remember that in quantum mechanics, quantities are measured by operators. For example, the position of a particle is measured by multiplication with the position operator, which acts on the wave function of the particle. You can think of the position operator as the meter. The meter tells you where the particle is. But this isn't the only way to measure the position of a particle. You can also take an observable that's related to the position, say the momentum, and measure that. This is possible because the momentum also tells you something about the position. You could also take another observable that's related to the momentum, and so on. These measurements are all related to each other. They're different ways to measure the same thing. And this web of relations between quantities that can be measured is called the observable algebra of a system. If you want to know what information falls into a black hole, you need to measure all the quantities that you want to know. And if you do this with a von Neumann measurement, then yes, information is lost. This is the result that Hawking arrived at. You can never measure enough quantities to get all the information back. This is because the observable algebra of a black hole is infinite dimensional. You can always find more observables that are related to each other and tell you more about the system. But that just means that the black hole has more information than you can ever measure. So some information must be lost. But here's the catch. The observable algebra of a black hole depends on the definition of the quantities you use to describe the black hole. And that's where the second category of definitions comes in. If you use a different definition, then the algebra can be finite dimensional, which means that you can actually measure all the information that you need. This is possible because in this definition, many of the quantities that you want to measure are unrelated to each other in a simple way. For example, if you want to know the spin of the electron, then the observable algebra that you need to measure the spin with is much smaller than the one that you need to measure the energy. So if you use the energy to infer the spin, you can get a lot of information out of it, whereas you wouldn't have been able to with the von Neumann measurement. These two different types of measurements can easily be distinguished, and that gives us a clear operational meaning of what it means to measure something. Namely, it's the information that you get out of a measurement. This operational definition doesn't depend on the details of the measurement, and it tells us that whether information is lost or not depends on how you choose to describe the system. This is why we needed to reformulate the question, what happens to information in a black hole? Because the answer depends on how you define information. You see, we usually think of information as something that's unambiguous. If you know the information, then you know exactly what's going on. But this isn't the case. For example, if you know that a particle is either spin up or spin down, that's information, but it's not very precise information. If you want to describe the state of the particle, you need to write down that it's in a superposition of spin-up and spin-down states. That's more information than you had before, but now the description becomes ambiguous. What does the particle actually do? Does it go left or right, up or down? We don't know because we haven't measured. If you want to know exactly what the particle will do, you need to measure it, which then gives you information. This is why you can never have complete information about a quantum system without doing a measurement. So there's no unambiguous answer to the question, what happens to information in a black hole? Depending on how you define information, you get different answers. If you use von Neumann measurements, then information is lost. If you don't, then it isn't. So both Hawking and his opponents were right, but only because they were asking the wrong question. Thanks for watching. See you next time.